Okay, I guess we can get started. So a week from today, we're going to have our first exam. It's going to cover everything since the beginning of the semester through whatever we go through on Thursday. The main goal for me is to see if you understand the concepts we've talked about so far. The questions will be mostly short answer. I may have you calculate a thing or two, but calculations aren't going to be the focus of the exam. I might have you calculate a couple of things related to what we've talked about specifically the last couple of classes, and then there will always be a follow-up that will be more conceptual in nature. So in terms of the exam, for those of you who are in class, just show up. You can bring a calculator. I think you asked me last time about whether I'd have equations on the exam. I'll give you all the equations, but I'm not going to explain what they are or how to use them or anything, but I'll just have the equation listed. You'll still need to know what the variables are and how to calculate things. So I don't know how helpful those will be, but like I said, the calculations aren't the main part of the exam, but to do real well, you'll still want to know how to do that properly. For those who are taking the test online, I will send a Zoom meeting invite to everybody. As soon as you log on, I will email you the exam, and then I want to be able to see you doing the exam on Zoom. I don't want you off somewhere else. I need to be able to see the area that you're working. If at any time your Zoom connection cuts out, I have to simply have you re-log in, and I will give you a different exam, and you'll have to start over. So make sure you have a secure connection, because we can't have people logging off and doing things that I can't see. I just need to ensure that the test is fair for everybody, and that the people at home don't have any advantage over the people who are in class, and vice versa. So if you have any questions on the exam, how it's going to go, let me know. Any questions now on it? Okay, let's move along. So this is going to be sort of the last day for a while where we really get into the physics of how water behaves. And this stuff's going to be really different. I don't think any of you have had any of this stuff before, okay? And we're going to use this when we talk about soils coming up in a couple weeks, okay? So actually, maybe even next class we might talk about soils. So what we're going to do is talk about how fluids behave. And like I said a class period or two ago, most of your experience in life has probably been with the fluid water. That's what you probably know and understand. And you've seen water. You've probably been swimming, you've been on boats, it comes out of your faucet, you clean with it, you cook with it. You have a lot of experience with water. But not all fluids behave like water does. And that's really what I want to concentrate on, because in the geologic world, we have lots of different kinds of fluids. And they behave really differently, especially things like soil. Soil you think is dirt, right? Most people, when I say, what's a soil? And your first sort of definition, it's the dirt. Well, it's actually really complicated. Soil has some solid particles in it, some rock fragments, some decomposing plant material, but it also has gases in it. It has water in it, and sometimes it can flow downhill like mud or like water. But it has a slightly different behavior, and that's what we're going to get into today. So what I have on this slide are two different fluids that behave really differently. Okay, water on the left, tar on the right. Now, in both cases, I have these fluids sitting on a slope. And gravity is going to act on these fluids. And remember back to last class, we talked about some physical parameters. We talked about force, okay? Force is mass times acceleration. All the stuff that you have sitting on the desk in front of you, it's being pulled down by gravity. Gravity wants to accelerate it down, okay? But the table is stopping it from moving. But if you're able to put your hand under your computer or under your water bottle or under your notebook, you'll feel that gravity is pulling that down. You'll feel the weight of it, okay? So force is the mass of the object. The more mass, the more force you have, times the acceleration. And when we talk about Earth things, that acceleration is usually due to the gravity of the Earth, which is 9.8 meters per second, okay? Stress or pressure is that force distributed over an area. If it's distributed over a big area, then you have less pressure or stress at the base. If all that force is distributed over a tiny area, I gave you that example of my shoe versus a high heel, then the stress or pressure goes up greatly. Okay? Strain is change in length of an object over the original length. And that's how materials respond to stress. When you stress something, they strain. Some things strain a lot under a given stress. Some things don't strain much at all under a given stress. And finally, strain rate is how quickly that deformation occurs. And that's what we're going to get into with this slide. So on the left we have water, and on the right we have tar. Okay? So if we let gravity do its thing, both of these materials are going to strain or deform or move to the bottom of the slope, right? They're going to move downhill and they're going to pile up on the bottom. The difference is the water is going to do it quicker. Tar is going to do it slower. So the strain rates are going to be different. They'll both strain the same amount. They'll both go from where they are to the bottom of the hill. They will both travel the same distance. So the strain is the same. But the rate of strain, how quickly that material moves to the bottom, is really different. The water moves a lot faster. Now if you put a third one up there with lava, it would move even slower yet. Or it might not move at all. We'll talk about why in a few minutes. So strain is equal in both cases if given enough time. But what's really different about these two is the strain rate. The strain rate for water is much greater than the strain rate for tar. So strain again is denoted by that little epsilon, and strain rate has the epsilon with the dot over the top. And this is just saying water moves faster than tar. It's kind of a fancy mathematical way of saying that. That's all it does. Strain rate for water is greater than the strain rate for tar if the stress is the same. And the stress is the same in this case because they're on the same slope. Okay, any questions on that so far? So these two fluids are different, aren't they? There must be something about them that makes water move faster than tar. We know they're made of different things, so maybe something about the composition allows water to move quicker than that sticky, pasty tar. Let y'all get caught up on your notes here. Okay, so like I said, just sort of a fancy way of saying water's going to move faster than tar on the same slope. Now in both of these cases, and what I have sort of listed here is that little sigma, that means stress or pressure, and that's coming from the fluid sitting on the slope. There's a stress, they want to move downhill under the influence of gravity. And it's saying it's proportional to strain rate. In other words, if I make the slope steeper, both of these are going to move faster, right? And if I make the slope less, both of them are going to move slower. So the stress is proportional to the strain rate. High stress, high slope means faster movement for both. But in all cases, water is going to move faster than tar, right? So mathematically, we can do this sort of proportion thing where stress is proportional to the strain rate. High stress, high slopes equal high strain rate. But again, the actual strain rates themselves will be different for tar and water. Another way to write this mathematically, and we do this all the time in math, is whenever we have a proportionality like that, where stress is proportional to strain rate, it may be possible to substitute in a constant where you can precisely calculate the amount of stress if you know the strain rate, and vice versa. So we have a constant for water, but it's obviously going to be different than the constant for tar because these move at different strain rates. They move at different speeds. So that's sort of a mathematical way of getting rid of that proportionality and getting an equal sign in there so we can actually do some math. This is an exercise that engineers strive to do all the time. Engineers want to know how strong materials are and how much they're going to move under different conditions. So this is kind of an engineering approach to environmental science. We want to know how natural materials are going to respond to humans messing around with them, putting structures on them, digging them, adding water to soils. How does that change all of this? We're really good at messing around with nature. And what we really want to do as scientists is be able to figure out as precisely as possible just how much is the Earth going to be impacted by what we do. So that's why we strive to come up with these mathematical equations where we can precisely calculate stresses and strains and movements. Okay, so we're at this point now where we have the stress. In both cases, the stress is from the fluid sitting on a slope. Gravity's going to act on these and try to pull them downhill. Water's going to move faster than tar if they're both on the same slope. We can rearrange this equation a little bit to give us that the stress is equal to the strain rate times some constant for water. And the same equation holds for tar, except we're going to have a different strain rate, or a different constant. As it turns out, and this is kind of where I'm getting with all this, that constant is the viscosity. It's actually a property that the water has, and that the tar has, and that all fluids have. Tar moves slower on the same slope, under the same stress or pressure, because it has a different viscosity. There's something about how tar is put together chemically that allows it to flow slower under the same conditions than water does. So tar and water will have different viscosities. So you can simply substitute in that viscosity symbol for the constant, and you have a really useful relationship where stress is viscosity times the strain rate. So if you know any two of those things, you can calculate the other one. If you know the stress and the strain rate, you can calculate the viscosity. If you know the viscosity, and we do know the viscosities for lots of natural substances, it's one of the things that civil engineers spend a lot of times doing, is measuring these different physical parameters. If you know the viscosity and you know the stress, you can predict how fast something will flow. And you can rearrange these equations to solve for any of those three variables: stress, strain rate, or viscosity. And I'll give you a couple of chances today to kind of play around with these equations and see what they do. All right, first of all, you know this is science and we do math, and in order for us to check our math and to make sure that we're doing it properly, one of the things we can do is look at the units and check the units. So I want you to try to figure out what the units are for viscosity. And then obviously in order to do that, you have to figure out what are the units for stress, what's the unit for strain rate. So the easiest way is to look at the arrangement of that equation that I have over here, right here. You can look at the units for stress. And then you have to look at the units for strain rate. And divide those through and see what you get. So you might have to look back at your notes from last class period or so ago. I'll give you a second to try to work through this. It's best to do that here in class, because if you don't do it right and you have questions, you can ask, and hopefully I can walk you through it. Okay, so we started with this little relationship right here, where viscosity is the stress divided by strain rate. If you go back and look at your notes, remember that we measure stress in a unit called pascals. Pascals are kilogram per meter second squared. And then we're dividing that by the strain rate. Strain rate, remember, is in per second. So we have per second on the bottom, and if you remember your mathematical skills, that when you have a second to the minus one on the bottom, actually ends up on the top. So the units that we use for viscosity are Pascal seconds. And that's the one I want you to remember. So we've calculated in the lab the viscosity of water at various temperatures. And here's a little value right here that we get for water at about 0 degrees C. And it's between 1 and 2 thousandths of a Pascal second, really low number. Water is very runny, so it has a very low viscosity. Okay, so let's try to use this here. I'll give you some values for other things, other geologic fluids here in a second. So water's viscosity, like most fluids, varies a little bit depending on different things. One of them's temperature. Water isn't very susceptible to viscosity changes when you change the temperature. Things like oil, if you know, when oil's really cold, it's super viscous, right? It doesn't flow very well at all. But hot oil runs much quicker. So oil has a highly temperature-dependent viscosity. Water changes very little with temperature. You heat it up, it changes a little bit, but not enough that we normally worry about it. But oils and lavas can change an awful lot depending on what temperature they are. As you know, water sometimes isn't fresh, pure water. Water's really good at dissolving things. And typically, the more stuff you dissolve in water, the higher the viscosity it has. So salt water will be a little less runny than fresh water. And the reason is that you're dissolving sodium and chlorine and all these different atoms, and they can be attracted to one another. And if they're attracted to each other, then there's little bits of weak bonding going on in your liquid, and that prevents it from flowing as easy. So you tend to have higher viscosity. Remember, viscosity and fluidity are opposite. If something's very fluid, high fluidity, it has a low viscosity. And if something has a low fluidity, doesn't move very well, low fluidity, it has a high viscosity. So high viscosity means it doesn't flow as easy. And that tends to happen when you dissolve things in your water, because the more dissolved ions you have, they can start attracting one another and preventing your water from flowing as well. If there's actual physical solid chunks in your water, if you think about a stream that's really muddy, it's muddy because there's little suspended sediment particles in there. And those little suspended dirt particles can bump into one another and can prevent your water from flowing as well. And if it's really full with dirt, then that's going to prevent your water from flowing a lot. At some point, you're going to have something that resembles more mud than water. And whenever those things bump together, they create friction that has to be overcome in order to get that fluid to move. So the more suspended particles, the lower your fluidity and the higher your viscosity. So temperature, dissolved species, and suspended particles can all affect your viscosity of water. Here's some viscosities of geologic fluids. I gave you water already. Between 1 and 2 1,000ths of a Pascal. Very low viscosity. Low viscosity means high fluidity. So water flows really easy. Mud, we sort of talked about mud. Mud is water with lots of dirt in it. And it can vary as to how much dirt. You can have really fine mud and you have really thick mud. If you don't have many dirt particles, then it's more like water than it is like thick mud. So your viscosity values can range from very similar to water. And then as you add more and more material to your mud and make it more thick and pasty, it can have viscosities up to about 10 pascals, or about 10,000 times more than just pure clean water. So those little particles can change the viscosity a lot. Basaltic magma, that's the stuff we have in Hawaii. It can be 100,000 to 1,000,000 times more viscous than water. So now we're getting into stuff that really doesn't want to move quickly at all. And then we get into some of our most viscous geologic materials. Rhyolite magma, this is the stuff that comes out of places like Mount St. Helens, a lot of these continental volcanoes. We're looking at billions to trillions of times more viscous than water. This stuff barely flows at all. You can put it on a steep slope and it might move a few inches in a day. Glacial speeds. And it just has a lot more internal bonding than some of the materials that have lower viscosities. So viscosity is the resistance to flow. You can think of it that way. All right. This is one of my favorite things to talk about. I love talking about how different kinds of fluids respond because we can use it in so many different ways. And I hopefully will get to the point today in class where we'll go back and try to use this a little bit to think about some real problems about the Earth. So I have a little diagram here. It's a little XY diagram. On the x-axis on the bottom, we have strain rate. So that's how fast the material is going to move. As you move from left to right, the material moves faster. And on the y-axis, up and down, we have stress or pressure. In this case, think about steepness of slope. Think about your fluid sitting on a steep slope. So for high stress, it'd be a really steep slope. For low stress, it'd be a very shallow slope. What if we don't have any slope at all? What if we're right here at the 0 point? What if we have no slope and we put water on it? Is there any tendency for it to move any direction? No. So the strain rate is going to be 0 too, right? What happens is we increase the slope. What happens to the speed of water movement? Yeah, the higher the slope, the faster it's going to move, right? So think about how tar and water would both plot on this graph. So they're both going to increase their speed of movement or strain rate with increased stress. But water is always going to move faster than tar on the same slope, right? So draw two lines that you think would represent, one line representing water and one line representing tar. See what you come up with. Then I'll put mine up and we'll kind of walk through it. All right, let's sort of build our plot here, okay? So if tar and water are both sitting on a flat slope, no slope, are they going to move? No, so they will both plot right here at the origin, right? So let's increase the slope a little bit. We have a pretty low slope right there. Which is going to move faster, tar or water? Water. So let's just put water, let's say maybe right here. And we'll use yellow. Tar's not going to move as much, right? Not going to move as fast. Tar's going to be over here. All right, let's crank our stress up to say right there. Now it's a much steeper slope, right? Which is going to move fastest? Water. So if water is there, where will tar be? It's not going to move as much, right? Not going to move as fast. So it's going to be here. And in fact, what you'll see is that for tar, you're going to get a slope that looks like this. And for water, you're going to get a slope that looks more like that. So this is going to be water. And this is going to be tar. I think I have this drawn out a little better on my next slide. There's water, low viscosity, moves really quick with very little slope. And there's tar. And all this is really saying is that in order to get tar to move really fast, you need a really high slope. You need lots of stress. And that's because it has a higher viscosity. Now, the way I've drawn this here is that both of these liquids have an increase in their movement, the strain rate. That's just how fast they're moving, when you increase the stress by maybe putting it on a steeper slope. But because water has a lower viscosity, it's always going to move faster than tar under the same conditions, under the same slope. So this shouldn't be too difficult for you. You're used to seeing water move. You've seen water move down a stream. You've seen water moving in your sink. Water moves downhill and it moves fast, right? And you've seen tar. You know how thick and sticky tar is. It doesn't move very well at all. So you guys are kind of used to these two. And what we've done up to this point is just sort of look at the mathematics of how stress and viscosity and speed of movement are all related. And this is kind of important, okay? When you're on a flat slope, neither moves, right? But anytime there's any slope, right? If you just crank the slope up a little, they both move, right? Water moves quick, tar moves slow. Put it on a 0.1% slope, just the most gradual of slopes. Water's going to feel that and move. So anytime there's stress from a slope, these materials will move. They might not move very fast. Tar's always going to move slower than water, but they're both going to move. As it turns out, that's not the way all materials behave, and we'll get to that here in a second. But just remember this, when no movement, the stress is zero. The general term that engineers give fluids that behave like tar and water is something called a Newtonian fluid. You guys know about Newtonian fluids. You're used to them. Alcohol flows this way. Water flows this way. Tar flows this way. Most of the fluids that you have experience with move this way. As it turns out, a lot of fluids out in nature don't behave this way. They're going to behave a different way. And we'll see what that is here on the next slide. All right, any questions so far? Newtonian fluids crank up the stress, and they will flow faster. Items that have higher viscosities will flow slower than those with lower viscosities. Like I just mentioned, a lot of materials that we have on Earth, though, don't behave this way. They behave as something called Bingham plastics. This is another engineering term. So we still have our same stress and strain rate diagram. I'll give you a second to draw this out. Okay, here is how Bingham plastics behave. I'm just going to put this up. Let you take a look at it. The yellow line is something like mud, or maybe basalt, which is the type of lava we have in Hawaii. And the red line is rhyolite. That's the super thick, pasty material that you find in continental volcanoes like Mount St. Helens. What's different about this plot than the plot for the Newtonian fluids that we had on the previous page? It doesn't start at the origin. Remember, the Newtonian fluids start down here, right? Look at basalt and mud. Okay? Now remember, stress you can think of in our situation as slope. That's where the stress is coming from in all the examples I've given you so far, okay? So when there's no slope in a Newtonian fluid, it doesn't move, right? And when there's no slope in a Bingham plastic, it doesn't move, right? But let's crank up the slope a little bit, crank up the stress a little bit to say right here. So now you have a real shallow slope. If water was sitting on there, what would happen to water? It's going to flow, right? What about lavas and mud? Is it moving? It doesn't move slow. It doesn't move at all. It will sit there on that slope forever. But it's a fluid. It's kind of weird, isn't it? Let's crank up the slope a little more, maybe to right there. Is it moving? When you hit this point right there, what happens to the basalt and mud? Starts moving, right? And look at the slope. Really low slope, right? The slope is viscosity. Once it starts moving, it actually starts moving really fast. So you have it on a flat slope, it doesn't move. Crank up the slope a little bit, still doesn't move. Crank it up a little more, still not moving. Crank it up enough, and it moves really fast. It's kind of weird, isn't it? But think about what mud is, okay? Think about mud. What's mud? What's that? Dirt and water, right? So what if it was like way, way, way more dirt than water, okay? You have tons of dirt and just a little bit of water. It's pretty dry mud. All of those dirt pieces are touching, right? And when things touch, they have friction that you have to overcome to get them to move. And think about a mud that is so thick that all of those dirt pieces are touching a lot. That gives you a lot of strength. It gives you a lot of stress that you have to overcome to get it to move. And that rubbing together of all those mud particles is enough to keep it sitting on certain slopes. Okay? But then once it moves, once you get it to break those little frictional attractions, it moves really easy. Now think about if your mud was really wet. You put more water in, right? You put more water in. Pretty soon if you put enough water in, you have more water than dirt, don't you? And at that point, those dirt pieces don't touch much, right? So what's going to happen as you add water to the amount of stress you need to get it to move? Eventually it's going to act more like water, right? Remember, water behaves like down here. This is water. So as you add more water, it's going to behave more like water. With the rhyolite, we still have to add in a lot more slope, right? You have to get this much slope before it starts moving. Once it moves, does it move very fast? No, it moves super slow, so it has a really high viscosity. The basalt and mud have a low viscosity. So viscosity is how fast it moves once it moves. But these Bingham plastics are different because you have to add a certain amount of stress to even get them to move. With water, any stress and they move. That minimum stress needed to get movement is called the yield stress, or yield strength. It's the minimum amount of stress, or in this case, you can think of as slope, that must be applied to get it to move. In other words, some fluids are strong. They can resist movement. So the strength is what separates a Bingham plastic from a Newtonian fluid. Bingham plastics have strength. Water has no strength at all. Any slope and it moves. It'll move under any stress at all. But a lot of earth materials have strength. And we're going to spend, like I said, a week or so talking about soils. Soils have dirt, but also moisture. And if you get them really moist, they act like a liquid with strength. But if you overcome the strength, that soil will move. If you build on soil, you don't want your soil to move. So we can actually start calculating what sort of slopes are needed to overcome the stress and allow soils to move and make land unstable. So that's kind of where we're going with all this. So Bingham plastics have a yield strength, which is the minimum amount of stress needed to get something to move. And then once they move, they also have a viscosity. Basalts and muds have low viscosity, so once they start moving, once you exceed their yield strength, they move really fast. Other things like rhyolite have a high yield strength, so it takes a lot to get them moving. And then they also have a high viscosity. Once they get moving, they don't move very fast. Okay, I'll try to give you some real examples here in a little bit. Any questions, though, so far? I'll let you get caught up on your notes. Okay. And again, just remember that in this case, both of these materials, they won't move until you have enough stress or enough slope to exceed the yield strength. And then, again, once they start moving, their movement is governed by their viscosity. Basalts and muds, low viscosity, they'll move quickly. Rhyolites have a high viscosity, they'll move slowly. All right. So basalt mud, low viscosity, low yield strength. Rhyolite, high viscosity, high yield strength. Steep slope, higher intercept on the y-axis for rhyolite. Mud has a low slope, which means low viscosity. On these graphs, the slope of the line is the viscosity. The yield strength is where it intercepts the y-axis. All right, this is kind of interesting. So let's say I have a canister of water on my tabletop, okay? And in both these cases, I'm going to pull away the canister and just let the fluid settle out, okay? Now we got to go back to the last class period. At the base of both of these, so if you're down here or down here, is there stress at the bottom of that? There's no slope, right? But is there stress from the weight of the overlying material? So if I pulled the can away from the Newtonian fluid, the water, what's it going to do? Pretend I have a coffee can full of water out here, and I just magically pull the can away. What's the water going to do? Spread out. Why is it spread out? It was confined and there's stress at the base, right? And we already know that this is a Newtonian fluid. Anytime there's stress, it moves, right? So how does it get to the point where it doesn't have any stress? It has to completely spread out, so it's basically just a molecule or so thick, right? So if you remove the container, the Newtonian fluid spreads out under gravity till it's only a molecule or so thick. But the Bingham plastic has strength. So it'll settle out, but then at some point, it's able, because it has strength, to hold up some of the thickness. So it won't spread out as much at all. It might only spread out to maybe this much. And it's just going to sit there. The weight of the overlying material isn't enough to exceed the yield strength and cause movement. Think of pancake batter. When you put pancake batter in the pan, it doesn't spread out as much as water does, right? You get, if you make it without much water, you can get a good centimeter thick pancake, right? It won't spread out anymore because it's got strength. All that flour in your pancake mix is rubbing against each other. It's not letting it spread out. And that happens with mud, and it happens with lava as well. Like you said, sandcastle? Yeah, if you put enough water, if you have a sandcastle and dump water on it, what happens to it? That water gets in between the sand grains and lifts them apart from one another, and then it doesn't have the same strength and your whole thing collapses. So yeah, sandcastle is held, it's not cemented together, right? It holds its shape because all those grains touch. They have friction between them. That's a great example, actually. Yeah, sandcastle is just loose dirt. The only thing that's holding it together is the little frictional attractions between the sand grains. And if you put a bunch of water in there, the water can get in the pore spaces and physically separate those so that they're not touching, and then the whole thing collapses. So it loses its strength as you add water. Great example. I'm going to use that in the future. So the Bingham plastic will settle until the stress from gravity is the same as the yield strength. So if you have something with a high yield strength, it'll actually be thicker. Think of your pancake batter. Less water, more flour grains touching, more strength, higher yield strength, doesn't settle as much. It's thicker. So if we go out in the geologic world, we can actually look at things that were fluid and look at their thicknesses and learn something about their engineering properties, how they respond to stress. And I'll give you some examples with lava here in a second, some photos that I've taken over the last couple of years. Okay, on the previous diagram, and I can't go back in my notes on this, but we had a stress strain rate diagram, and we had how do I get this back? I can't. Excuse me, I screwed this up. All right, let me get this back. Okay, so again, we have these two different fluids. If we remove the canister and the Newtonian fluid, it's going to settle out, because anytime it's under stress, and the stress can just be from, in this case, the weight of overlying material, it's going to spread out to a molecule or a couple molecules thick. But the Bingham plastics have strength to them. So they will resist flow, much like the pancake batter example that we had. Now, in this next slide, I've got a photo of some lava flows, okay? And on our previous example, we talked about how things can settle out, okay? So this is a rhyolite lava flow, and you can see how thick it is, right? This is pretty thick material right here. A couple 100 feet, because here's some trees over here. That's how thick that flow is. That flow is 100, 150 feet thick. It's kind of cool lava flow. If you go there, all this dark material right here, this is obsidian. So you'd be able to go there and just be glass on the surface. This is Newberry Volcano in Central Oregon. It's a national monument or national park, so you can go visit it some way. But it's a lava flow that has a very high yield strength, so it doesn't get very thin. And if you're watching this flow, it would flow about this much a day, a foot or two. So super high viscosity, super high yield strength. Compare that thickness and movement to something in Hawaii. So here's Hawaii, and you can see how thin the lava is here. It's just a foot or two. So much lower yield strength. And you can actually watch this stuff flow pretty fast. I mean, it'll flow at times at a walking speed. You know, so it can flow a couple 100 feet a day easily. So much lower viscosity, much lower yield strength. All right, do you guys have any questions? Okay, let's let's go ahead and stop that. All right, take a break for a minute or three, and let me get the next thing all queued up here. Okay, we can start looking at soils based on what we've already talked about here a little bit. So just a few review terms. We've talked about most of these today already. So we're going to talk about what soils are, why they're important, and how they respond to stress and change that humans impart upon them. As humans, we mess with our soils a lot. How do we use soils as humans? Can you give me some examples?
Plants.
What's that?
Plants.
We plant stuff in it, right? Okay, so soils are really important if you're in the agriculture business. A lot of our food comes from growing plants or growing plants to feed animals that we then eat as well. So soil is really important in agriculture. Besides agriculture, what else do we use soils for? We build stuff in them, right? We build houses, we build roads, we build bridges, and in every case, we want our structures to last, right? I don't know if you've ever driven down a highway that was built over poor soils. Just bumpy the whole way. And that's from the soils expanding beneath the road or stretching beneath the road or flowing or moving beneath the road. We have soils in earthquake country that lose all of their strength when they're shaken. It's a process called liquefaction. When soils are disturbed, they might lose all their strength. If a soil doesn't have any strength and you have something built on it, what happens to the thing that's built on a soil with no strength? It collapses. And we've had bridges that have collapsed under soils that were disturbed by earthquakes. I'll give you some examples of that in this chapter. So, understanding how soils respond to stress and pressure are pretty important. So, just to review some terms, stress is force divided by area. We talked about that a little earlier today. We measure stress in pascals. Pascals can be thought of in Newton per meter squared or kilogram meter per second squared. You can go back and look at your notes and see how all those units work out. We've talked about stress so far as just being pressure. And in the examples I've given you so far, the stress that initiates the movement of our liquids usually comes from sitting on a slope. But we're going to look a little closer at stress. There's different types of stress. And in geology, we talk about 3 different types for the most part: compression, tension, and shear. Earth materials respond really different to different types of stress. I think I mentioned it once in an earlier class that rocks are really strong when you try to compress them. Try hitting a rock with a rock hammer. In order to break it, you have to hit a rock really hard. So they're really strong under compression, but they're really weak under tension. And a really good example of that, how many have been to Mount Rushmore? You guys been to Mount Rushmore? You know, the great carvings of the president? Well, every summer, Park Service workers go up and they hang off of ropes on those faces, And they fill every crack they can find on Abraham Lincoln's nose or George Washington's ear or whatever. Any crack they can find, they fill it with putty. And the reason is that if water gets in there and freezes, what does water do when it freezes in terms of its size? It expands, right? So think about a crack in a rock. If you put something in that expands it, you're putting it under tension, right? You're prying it apart. Rocks are super weak under tension. They only have about 1/10 the strength as they do under compression when they're under tension. So rocks break really, really easy under tension. If you want to break a rock, try to pry it apart. If you find a crack, jam a crowbar in there and start yanking, it'll break real easy. Much easier than trying to beat it to pieces with a rock hammer. You have to add about 10 times as much stress by beating it as you do by putting it under tension or prying it apart. And then under shear, rock is pushed in two opposite directions. So if you watch WWE or something like that, compression is basically being punched in the face. Tension is having your ears pulled apart. And if somebody takes their hand and rakes it down your face, that's going to be shear. It's all different stress put on you, but in a very different way. Tension, you're pulling apart something. Compression, you're squeezing it. Shearing, you're sort of squishing it sideways so that the rock is pushed in sort of two opposite directions. And geologic materials respond really differently depending on which of these types of stress it's experiencing. The other thing to keep in mind is that not only rocks, but pretty much every material bends before they break. Take a pencil and flex it. It always bends, and if you bend it enough, it snaps. Happens with metals, happens with rock. Rocks will bend a little before they break. So if you put stress on something, if you put just a little bit of stress on it, and it has a strength, maybe nothing happens. Yeah. Put enough stress on, maybe it bends a little. And if you put enough stress where you exceed the strength, then it's going to break. So that's how materials respond to the stress that we put upon them. And as I mentioned a second ago, geologic materials, rocks and soils, tend to be very strong when compressed and very weak when they're pulled apart. So that's something we're going to look for as well when we evaluate how humans mess with land. We really want to have our eyes open for situations where we create tension. Because our rocks and soils aren't going to stay very strong. They're not going to be very stable if we create situations that put the rocks under tension. We want to try to keep them compressed as best we can. Okay, so I have a little diagram here for you. A little slope. So, see the black line? Everything under the black line is solid rock. The area between the black line and the gray line is soil. So, loose dirt material. Is there stress on the soil? It wants to move downhill, right? Yeah, gravity's acting on it. So yeah, gravity's pulling it down a slope. So there's stress on it. But the soil particles are going to be touching one another, so it's got some strength too. If the material isn't moving, then we know that the soil has enough strength to counteract the stress that it's experiencing from sitting on that slope. What if we increase the slope? Then we increase the stress, right? And we make it more prone to movement. All right, let's say you buy land. It's hard to buy land that's perfectly flat. Maybe if you live in Iowa. But even Iowa has some old hills from the past ice ages. It doesn't really matter where you go. There's not a whole lot of places that are perfectly flat. And especially out here in the West, you'd be hard-pressed to find anything that's flat. But when we build houses, we do not want the crooked man and the crooked house, crooked wife and the crooked dog. So what we do is we tend to carve out these notches where we can make a perfectly flat little piece of land to put our house on. We just messed with nature, didn't we? It just looks like a simple notch. But you'd be surprised at how much this changes things. So let's think about this for a minute. Okay, one thing I don't know if you caught is you see the line under the house is green. Because what do people do when they put in houses? They put in grass. And you got to water that stuff, right? So yeah, if you want water to grow, especially around here, you're going to want grass to grow around here, you're going to be watering it. We've already talked about what water does when it gets in soil, right? It gets into the little openings and it can separate those dirt pieces that are touching, and it can lose its strength by doing that, right? It also adds weight. Water's heavy. We talked about how heavy water is. A cubic meter of water weighs a ton. So think about watering the grass. You know, let your water run for an hour or two. How much of that cubic meter are you going to fill up? You can fill up some of it, right? Dump that on your grass, on your soil, and you add a lot of weight to it. That increases the stress, doesn't it? So how does the building of this house affect the stress? Okay, we already talked about the fact that we're going to put water to grow grass, right? It's going to make things heavier. What about uphill from that notch? You made a notch, right? Well, that right there. Everything uphill from that now. Does it have any real support? No, so the tendency is going to be you just weakened it, didn't you? Because you made a 90-degree slope, right? Right there it went from, maybe 15 degrees to that little notch there as 90 degrees. That's not going to stay a perfectly vertical notch for long. It's going to crumble, isn't it? So maybe you end up building what they call a retaining wall. You can move in rocks, timbers, to try to hold back, because this soil wants to move, right? And now that you have this notch here, you don't have any support. So you greatly increase that local slope. You remove that notch. So this material down here is going to start moving, right? And it might start pulling away from the upper. And you might start creating these areas of tension and cracks, right? Because now it's under tension. You're pulling it apart. Rocks are weak under tension. So you make cracks. Maybe lots of cracks. What's going to get in the cracks? Water, which adds weight, which reduces the strength, which speeds up the movement, doesn't it? So the water can get into these cracks, reduce the strength, add weight, which makes even more cracks. Typically, when you notch stuff out, it creates tons of problems. Retaining walls are expensive. And every time it rains, the tendency is for the stuff to move downhill even faster. So water can get into those cracks, which makes it heavier, which reduces the strength, which makes it move even more, which creates more cracks, which allows more water in. So just by making this simple notch, you create lots of instability uphill from your house, exactly where you don't want the instability, right? Because where's this material going to end up if it goes downhill? Right on the house. The house and the yard add even more stress. As we said a second ago, the water can reduce the yield strength of the soil, which allows it to move even more. So you notched it, you put in a yard, a house, you added water, and the net result is that you really weakened everything that's going on uphill because you changed the stress. You allowed that lower part near the notch to move quicker than the upper part, and that gives you areas that start pulling apart from other areas. That creates cracks, more water gets in, and the whole process sort of accelerates. Okay, so we'll end there and talk about what soils really are next class, but I just wanted to sort of put this out there to relate our soils to some of the strength stuff we had talked about a little earlier. So remember the exam in a week, and if you have any questions, send me an email, set up a time to talk to me, whatever works for you.